Hello everyone and welcome to this class which is dedicated to defects in crystalline materials. It is given in the frame of the course Materials and Their Properties offered by the Federal University of ABC, and I'm Professor Mathilde Champeau. So up to now in this course we assume there is a perfect order in crystalline materials. But the reality is quite different. A perfect order does not exist. All crystalline materials contain various defects. And in fact, various properties will be dependent on these defects, so their concentrations, the kind of defect. And so defects are not always adverse, and often specific characteristics are deliberately fashioned by the introduction of a controlled amount of defects. And so we are going to see the different crystalline defects. So what do we mean by crystalline defects? We mean lattice irregularity, or in other way, lattice imperfection. So we are going to see four kinds of defects. The point defects that are associated with one or two atomic positions, the linear defects that we are going to call dislocations, the interfacial defects, and the bulk and volume defects. So the objective is to describe these different kinds of defects, and to introduce some relationship between defects and some materials properties to see how we can benefit, how we can obtain specific characteristics by introducing defects in our crystalline materials. So the first kind of defect that we are going to focus is the point defects. So first of all, let's consider this case study that focuses on lithium-ion batteries. And there is research that has been performed by some researchers from Rice University that show that in fact we can improve lithium transport in battery cathodes that are used, for example, in your cell phone and so on, by introducing some defects. And so if you read this, if you read this all materials that is presented on this link, then you can understand a little bit better. But basically, they observed they observed superior transport properties in this lithium battery, and they analyzed the cause of this improvement, and they saw that in fact there was some point defects, which are atoms misplaced in the crystal solid, and they were not able to eliminate these defects during the fabrication process. But in fact, they observed that it turns out that they make really weird electronic materials behave very differently from perfect crystals, and that they have, in fact, better transport properties. And so basically, these defects allow to increase the reactive surface area. And so there was a more efficient exchange of lithium ions between the cathode and electrolyte in this battery. So to summarize, by introducing or by having these point defects formed during the process, the fabrication of this battery, of this material, they observed better transport properties and so better performance for these electrodes. So let's have a look to how does a lithium-ion battery works. So here is a representative scheme of a lithium-ion battery. So in fact, you have a positive electrode, which is the cathode, that contain lithium metal oxide. You have a separator, which is a permeable membrane to ion. And you have an anode, which is the negative electrode, that is comprised of graphite. And so what is occurring during the charge of the battery? You have the lithium ions that are migrate towards the negative electron, and so they store electrons from an external energy sources. So the lithium ions become lithium atom, neutral one. And so after that, when you use your lithium ion battery, for example, to use your cell phone, so the lithium will lose electrons that are used on your cell phone to make it work, to furnish energy. And the lithium ions now migrate to this cathode. Okay, so this is how it works. And so basically, to make the relationship with the studies that we saw in the previous slide, by introducing point defects in this material, so it favors this transport of the lithium ions in your battery, and so it improves the performance of your battery. And so we are going to see that this is the kind of defects that are formed in our lattice structure. As you can see here, right here, an atom is missing, and this kind of open vacant space in the lattice are responsible for an improvement of the lithium ion transport. So now let's explain, in fact, what are the two kinds of point defects that we find. So we are going to see that we have vacancies and self-interstitial defects. So the first defect, vacancy, as you saw, is the one that we have already described. So there is an open position here, or a position in which an atom is missing. And self-interstitial, we have another atom, added atom, within the lattice. So first of all, let's focus on the vacancy, or vacant lattice sites, which is an absence of an atom at one point of the crystal lattice. So it is formed either during solidification of the material, or during atomic vibrations that cause the displacement of atoms from their normal lattice sites. And so we can calculate the number of vacancies in a material. So here you have the equation. And as you can see, the number of vacancies is dependent on the temperature. So in this equation, we have the number of vacancies that is equal to the number of atomic sites, exponential minus the energy required for the formation of a vacancy, divided by the Boltzmann constant times absolute temperature. And so if the temperature increases, this exponential will increase, and so the number of vacancy will increase exponentially. So you can make some calculation and compare, and so see the evolution of this number of vacancy. The second kind of point defect, as we saw, is the self-interstitial defect. It is an atom that is inserted into an interstitial site, which is a small space that is normally not occupied. And this kind of self-interstitial, this atom placed in self-interstitial space introduce large distortion in the surrounding lattice. So if you have a look on this microscopy, you can see all the atoms that are organized in this crystal lattice. And here on that point, specific site, there is this self-interstitial atom. And this self-interstitial atom causes distortion right here of the arrangement of the atoms. Okay. So let's consider a case study. Let's consider silver, 100% pure silver. So pure silver is highly corrosion resistant, which is a property that is very useful in many applications. But the problem is that it is very soft. And so in the application that require high mechanical stress, we need to find a solution to keep the good corrosion resistance of this material, but that's unable to improve this mechanical strength. And so a possibility is to incorporate a small amount of copper, precisely when we add 7.5 weight% of copper. So we keep the good corrosion resistance of silver, and we improve the mechanical strength. So here we add a determined amount of what we call impurity atoms. In that case, it is copper. And these impurity atoms, we also call it alloying elements. So in that case, we have 7.5 weight% of alloying element, which is copper. Okay, so here we introduced what is an alloy. It is a metal that is composed of more than one kind of atoms. But in fact, so a pure metal, 100% pure metal doesn't exist. The maximal purity is 99.99 and so on percent. So in fact, we have 10 at 22, 10 at 23 impurities per cubic meters. So to conclude or to summarize, impurity or foreign atoms are always present. Either they are substitutional, either they are interstitial. And in metals, impurity atoms intentionally added are called alloying elements, as we saw in the case of silver and copper. And its purpose can be to increase mechanical resistance, like in the case of silver, in which we introduced a small amount of copper. Or we can also add an alloying element to improve the corrosion resistance of a material, or to improve its electrical conductivity, and so on. So many applications or to tune some properties of materials, we can incorporate alloying elements. So these impure metals are called alloys. Okay, now let's consider this second case study. So as you may know this Golden Gate Bridge in San Francisco. If we consider what are the requirements for a bridge, it must be made of a very strong material to support the weight of so many cars over such a long distance. And so one material that is relatively cheap is iron. But the problem is that iron is not particularly strong. And so in order to improve its mechanical property, we add a small amount of carbon impurity atoms. Okay, so in that case, impurity atoms is carbon. And as you can see, the weight percentage of carbon is really low. It's about 2.14 weight%. And only this small amount of carbon atoms enable to increase a lot the mechanical resistance of iron. And so by adding this small amount of carbon, we create steel. So this alloy is called steel. And so if we have a look to the diameter of iron and of carbon, we will see that the diameter or the radius of carbon is much smaller than the one of iron. And so carbon atoms will be able to fill the interstitial sides in the iron lattice. Okay, so here is a representation of this crystal lattice of iron, which is represented in red, and in blue are represented carbon atoms in the interstitial sites. And so we say that carbon is an interstitial impurity atom. Let's go to another case study. We are going to introduce semiconductors. So I'm sure you have heard about semiconductors that are used in electronics. So they are solid substance that has a conductivity between that of insulators and that of conductors. And this intermediate conductivity is either due to the addition of an impurity, or it is provoked by temperature effects. So the conducting properties of semiconductors may be altered by the deliberate, controlled introduction of impurities called doping into the crystal structure. So let's consider a silicon, pure silicon material, or almost pure, right? A silicon material and its crystal lattice. So if you have a look to the electronic configuration of silicon, so it has 4 valence electrons and it is able to form covalent bond with the neighbor atoms. And so as you can see, each silicon is covalently bound to 4 other silicon neighbors. And in that way, since all the electrons of silicon are involved in covalent bonding, there is no free electrons. And so as we will see in some, as we will see later in this class, the free electrons are responsible for electronic conductivity. And so in that case, silicon is not able to conduct electricity, so it is an insulator. And so very basically and very rapidly, and later we will be able to explain it, by making the substitution of one silicon atom by one phosphorus atom in the lattice position. So we substitute one silicon atom by one phosphorus atom in the lattice. This changed totally the electrical properties of the silicon, and it turns to be a semiconductor, okay, by the introduction of this phosphorus. And so phosphorus is called impurity, or substitutional impurity, or doping, since in that case it's increased the electrical conductivity of silicon. And so here we introduce substitutional impurity atoms. So when impurity atoms are added to a metal, there will be formation of either a solid solution. So in that case, the addition of atoms does not modify the crystalline structure, nor causes the formation of new structures, or there is formation of a second phase, which is a region of different composition and or different structure. And the formation of either a solid solution or a second phase will depend on the kind of impurity, which means the kind of atoms that are introduced in the composition, their concentration, and also the temperature. So here you have schematic representation of a lattice structure of gray atoms that are majority. And you can see that the orange atom is the impurity. And in this part, in this region of the crystal, in fact, you have no modification of the crystal structure, and you don't have formation of new structure either. So in fact, in this region, we have what we call the formation of a solid solution. And differently, in this part of this material, you have a higher concentration of the orange atom, of this impurity atom, and a formation of a different structure, as you can see. So the crystal structure is different, okay? The organization of the atoms is different. And so we say that a second phase has been formed in this region, okay? And so in an alloy, the element which is present in a minor concentration is called solute. And the element present in major concentration is called solvent. So it is very similar to what you may have studied in chemistry. So you have the solvent that dissolves the solute, okay? So we use the same vocabulary. So a solid solution has an homogeneous composition. So the impurity atoms are randomly and uniformly distributed in the solid. And this is quite similar to liquid solution, where we mix the liquid A and the liquid B, and that form a completely homogeneous solution. So the idea is very similar. In the case of solid solutions, we have homogeneous compositions. And so two kinds of defects can be found in solid solutions. So either substitutional, which is the example of the silicon superconductor with some phosphorus atoms that have been added and that we introduced. So basically, this is a substitutional solid solution. And there are also other examples, for example, brass, which is copper and a certain amount of zinc, so 37% of zinc. Bronze also, mono, and so on. So there, a lot of alloy are substitutional solid solutions. And we also have interstitial solid solutions, so in which the solid atoms occupy interstices in the lattice. So we saw the example of the steel bridge, and in which a small percent of carbon occupy interstitial position in iron lattice. And so steel is an interstitial solid solution. So for the case of substitutional solid solution, in order to know, to determine the degree to which the solute will dissolve in the solvent, so there are four criteria or four solubility rules, either called Hume-Rotary rules, that should be considered. So the first one deals with the atomic size factor. So the difference between atomic radii of the two types of atoms, solute and solvent, should be lower than 15%. Otherwise, the solute will create substantial distortions in the network and a new phase will be formed. The second point is related to crystal structure. So the crystal structures for metals of both atom types must be the same. So the solvent and the solute must have the same crystal structure. Then we should consider the electronegativity. So solvent and solute must have similar electronegativities in order to favor the formation of a substitutional solid solution. And finally, the valencies of the two atoms are very important. So higher solubility are achieved when the solute atom has a higher valency. So we have a higher contribution of the electrons of the solute in the metallic bond. Okay. And so if we consider this example of copper and nickel, and if we have a look to these four criteria, these four rules, we will see that considering the atomic radius, they have similar atomic radius. Their crystal structure are the same. They have a FCC crystal structure. Their electronegativity are similar. So for copper, it is 1.9, and in the case of nickel, it is 1.8. And finally, considering the valency, the copper has a +1 valency, and nickel has 2 valence electrons. And so since these two elements fulfill the 4 solubility rules, we observe that they are completely soluble in one another at all proportions. So either copper is a solute element and nickel is a solvent, or the contrary, and they are completely miscible. They will form a substitutional solid solution at any proportion of these two atoms. Regarding interstitial solid solutions, let's remember we have the impurity atoms that fill the voids or interstices among the solvent atoms in the crystal structure. Considering the atomic packing factor in metals, when the atomic packing factor is high, so the space available for this this solute atom is rather low. And so we have to consider the diameter of this solute atom that must be really smaller than the one of the solvent atom. Also, in interstitial solid solutions, we will rarely find a concentration of interstitial solute higher than 10 atomic percent. And also considering this dimension of this diameters of the solvent atom and solute atom, so the introduction of solute atom generally will introduce some lattice distortion of the host atoms. And so because of this distortion and this strain introduced in the lattice of the solvent atoms, so we have higher impact, and this is related to a higher impact on mechanical properties if we compared with substitutional solids. Let's have a look to the interstitial sites found in FCC crystal structure. So in FCC crystal structure, let's remember we have an atom at each corner of each face or each corner of this cube, and one atom placed at the center of each face of this cube. And we will define two kinds of interstices. The first one are tetrahedral interstices, and the other one, the octahedral interstices. So the tetrahedral interstice is formed at the center of the tetrahedron that is formed by 4 atoms. These 4 atoms are one atom at a corner and 3 neighbor atoms that are placed in the center of these faces, okay, of this cube. And so this tetrahedron have at its center a tetrahedral interstice that can be filled by the solute atom. In the case of the octahedral interstice, it it is formed at the center of an octahedron. This octahedron is formed by 6 atoms that are the ones that are located at the center of each face of this unit cell. Okay, and so at the center of this octahedron, we have an octahedral interstice. And so by applying this definition and finding the different tetrahedral and tetrahedron and octahedron in the unit cell, so you will find the number of octahedral and tetrahedral interstices in your crystal structure. So this was the explanation of the tetrahedral and octahedral interstices in the FCC crystal structure. Now, if we consider the BCC crystal structure that is formed by one atom at each corner of this unit cell and one atom at the center of this cube, we also find tetrahedral and octahedral interstices. So tetrahedral interstice is formed at the center of this tetrahedron that is formed by two atoms that are along the same edge of the unit cell, and one atom that is placed, the one that is placed at the center of this unit cell, and the equivalent atom that is placed in the center of the neighbor unit cell. Okay, so as it is represented on this figure, we have a tetrahedron, and so the center of this tetrahedron is a tetrahedral interstice. And so you can see that we find many tetrahedral interstices in the BCC crystal structure. Regarding the octahedral interstice, it is formed by 6 atoms. So we have the 4 atoms that form a face of our cube, of our unit cell, and the atom placed at the center of this unit cell, and another atom that is placed at the center of the neighbor unit cell. So it forms an octahedron, and so at the center of this octahedral, we have a octahedral interstice. Okay, that can be filled by the interstitial atom. So finally, when we are talking about solid solutions, as we saw, it is very important to define the composition of the alloy. And there are different ways to express this composition. So the first one, we express it as a concentration by weight, which is the weight of a particular element relative to the total alloy weight. So it is calculated in that case for the concentration by weight of A as the weight of A divided by the weight of all the different elements in the alloy. And it is expressed in percent. Okay. We can also express the composition of an alloy with the atomic concentration. So in that case, it is the number of moles of an element in relation to the total moles of the elements in the alloy. So in that case, the atomic concentration of the atom A is equal to the number of moles of A divided by the sum of the number of moles of each element of the alloy. And it is also expressed in percentage. So now let's go to linear defects that we are going to call dislocations. First of all, let's focus on this case study. Here we are going to introduce or to understand what is occurring during a thermomechanical processing of metals that is performed at relatively low temperature. So we call it cold working, and there are 2 techniques that are commonly used. One is forging, one is rolling. So in the case of forging, you have a blank piece of metal that is put into a die. There is a force that is applied by the mold, And as you can see, the metal is deformed. And if we open the mold, we will see that the shape remains. And so when we deform and the shape is kept by the material, so we call it, we say that it is plastically deformed, okay? When the deformation is permanent, we say it is a plastic deformation. So it is the case of forging. It is also the case in rolling. So in that case, we have metallic plate that pass within two rolls. And so you can see that the opening thickness between the two rolls is lower than the thickness of the original plate. So these two rolls will apply a shear force on this plate. And so the thickness of the plate will decrease between the rolls and it will remain plastically deformed. Okay. So in these two cases, during this plastic deformation, what is occurring in the material? So if we use a technique that is called electronic microscopy, that is a kind of microscope that instead of using a light, used electron, we are able to observe at a very low scale what is happening in the material. Okay, and in that case, it is a titanium alloy that has been cold worked, and we observe a lot of black lines in these materials, and these black lines corresponds to dislocations. And you can see that in some aspects, this line entangle, okay? They begin to, they encounter one with another. This is due to the fact that during the process, during deformation, in fact, this dislocation, they are able to move in the material in order to permit this plastic deformation, okay? However, when there are too many dislocations, they begin to entangle, and this entanglement hinder their movement in the material. So once these dislocations are so many and they don't move anymore, so the material cannot deform anymore. So in fact, what happened during the process, we controlled the dislocation, the number of dislocations, in order to get a final material in which there are so many dislocations that during the use of this material, their movement will be hindered. And so during the use of the material, no more plastic deformation will occur. So for example, this kind of titanium alloy after cold working are used for hip prosthesis. In the case of hip prosthesis, since the patient will have to walk every day, and the hip prosthesis will be submitted to cycles of loading and loading, loading and loading during days and years. So we need to ensure that this titanium prosthesis has a good resistance to fatigue. So later we will introduce what is fatigue. But in fact, we use this process to control the number of dislocation in order to have a titanium implant that will have a good resistance to fatigue due to this entanglement of dislocation. So we introduced dislocations, and we saw a very nice example of how it is used for the beneficial of the application. So now let's understand a little bit more about dislocation. So it is a linear or one-dimensional defect around which some of the atoms will misalign. So in general, they are introduced in the crystal either during solidification of the material, either, as we saw in the previous example, when the material is permanently deformed or plastically deformed. And so they are useful in order to understand plastic deformation in materials, and, for example, to increase the mechanical strength of metallic materials or their fatigue resistance. So here you have another example, which is a single crystal of zinc that has been plastically stretched, and you can see many, how can I say, different parts of this crystal that seems to have dislocated one from another along these planes. Okay, so this is due to the fact that dislocation have been created, and visually we can observe this plastical deformation and this creation of this dislocation. So in the lesson dedicated to mechanical properties, we will come back to this subject. So there are two types of dislocations, the edge dislocation and screw dislocation. So first, let's focus on edge dislocation. So this defect occurs either due to the presence of an extra plane of atoms. As you can see on this representation, we have 4 normal planes of atoms, this one, and this one, and that one, okay? And it seems that there is an extra plane of atom right here. But in other case, we could also say that there is a loss of a plane, half a plane, in fact, of atoms, okay, in the middle of the lattice. So we have an extra half plane of atom or loss of a half plane of atom. And this kind of edge dislocation causes some localized lattice distortion. As you see in this representation, so we have this half extra plane of atoms, and so the atoms that are close to this extra plane seems to be squeezed, one in relation to another, squeezed together. And so in fact, since they are squeezed together, they are under compression, whereas these atoms that are below this extra half plane, they are pulled from another, and so they are under traction, okay? And so this effect of compression and traction in the lattice will decrease with the distance from this extra plane. So for example, in that part of the lattice, the deformation, compression, traction that is felt by these atoms is much lower than the closest planes to this half plane of atoms, okay? And so we introduce dislocation line. So what is dislocation line? It is defined along the end of the extra half plane of atoms, okay? So it is represented right here, or in this example, it is represented by this sign, perpendicular. And so in the case of edge dislocation, this dislocation line is perpendicular to the slide. And this symbol also indicates the position of the dislocation line. Okay. And the other kind of dislocation is screw dislocation. So in that case, the defect occurs when the planes of atoms in the crystal lattice trace a spiral path around the dislocation line. So in that case, it seems that the material has been submitted to shear stress. And so we have the dislocation of lines of atom around the perpendicular dislocation lines, okay? So if we have a look on the top of this dislocation, okay, we will observe that the atoms on the bottom of this dislocation are at specific positions that are represented in this scheme as black dots, and the atoms of the upper part of the dislocation lines are represented as white points. Okay, and if we have a look above this dislocation line, like it is represented right here, we observe that at a certain distance of this dislocation, the atoms of the below plane and upper planes superimpose one to another, but close to the dislocation line, which corresponds to this line A to B, they have a certain distortion, okay? And in fact, the atoms from the plane from below this dislocation line and above the dislocation line, at that position begins to superimpose, but in fact, the distance between these atoms that were that superimposed but that were shifted is now equal to an interatomic distance. Okay, so just to repeat once again, the dislocation line in that case is perpendicular to the plane we observed on this figure, and so we introduced edge dislocation, screw dislocation, but in fact, in many cases, we will most dislocations found in crystalline materials are mixed dislocations. So they are not 100% screw dislocation or 100% edge dislocation, but they are mixed dislocation. So here is an example. You can see that this dislocation is much more complicated than the two perfect cases that we studied in the previous slides. So the dislocation line is between A and B, and we have a part of this dislocation that can be explained by screw dislocation, like we observe right here, and edge dislocation that we observe much closer to B, to the B point. Okay, so we introduced a mixed dislocation. So in order to understand this dislocation, we use a tool that is called the Berger vector. So in fact, it describes the magnitude and the direction of the lattice distortion associated with a dislocation. So in order to find and to define the Berger vector, we use the Berger circuit. So what it is, you will trace a circuit, a continuous line between the atoms that surrender the dislocation. Okay, so let's start from A, and you will have to trace this circuit, continuing the line around atoms that are spaced by the same interatomic distance. So here A, go to this atom, these atoms, and so on, up to B. Then, since we want to create a circuit, closed circuit, so we have to go in the vertical direction. So it's go from B to C, and then you come back respecting this interatomic distance, so you come back in the direction of D, and to close this circuit, so from D to A. Okay, so we have a closed circuit. Okay, so in that case, if you count the distance between A and B and C and D, the distance will be the same. So it will be the same number of steps that you will have performed. And in the case of B to C and D to A, Also, it is the same number of steps that you will have traces. In the second case, so you can do the same, and you will see that in that case, the distance between A and B and C and D is the same, but the distance between B and C and D and A is different. So the distance D to A has one more path than the one from B to C. And so, in fact, this additional vector is what we call the Burger vector. So as you can see, the Burger vector is represented by a small letter B, and it is a vector, so it has a direction. So that's why we don't forget to represent, to write here with a small arrow above like a representation of a vector. Okay, so this is the Burger vector that we use, and so it represents the magnitude of this vector, represent the lattice distortion, and its direction indicates also the direction of this lattice distortion. Okay, so now if we come back to the edge dislocation and screw dislocation and try to identify the Burger vector, we will see that in fact, in edge dislocation, if we trace the Burger circuit around this dislocation, edge dislocation, we will see that we will be able to identify the Burger vector B, and this Burger vector is perpendicular to the dislocation line. Okay. So the dislocation line that is right here, and let's remember that the symbol used to represent the dislocation line in the case of edge dislocation is the symbol of perpendicular. In the case of screw dislocation, it is quite different, because if we trace the Burger circuit, we will see that in fact the extra distance of in the circuit, which means the Burger vector, is right here. Okay, and so it is parallel to the dislocation line that is in that direction. And let's remember that the symbol to represent the dislocation line in case of screw dislocation, it is circular arrow. Okay, so I could represent right here with this symbol, this circular arrow, the presence of the dislocation line. Okay, and so in metallic materials, the magnitude of the Burger vector is equal to the interatomic spacing. Okay, which make it quite easy. So if you want to have more information, if you want to see a demonstration of how we determine this Burger circuit and Burger vector, so you can click on, or you can visit that link that explains step by step how to find it. Okay, so we presented a dislocation. We saw the Burger vectors that enable to express the magnitude and direction of the lattice distortion. And now let's consider what is happening with this dislocation. So as we show, or as we explained in the previous example, we saw that during plastic deformation, there is a movement of this dislocation. So if we have a look to edge dislocation, so as it is represented right here, if we apply a force that is vertical, okay, vertically applying to this metal, so this edge dislocation will move, it will shift in the crystal, and the dislocation area will move parallel to the direction of the stress. Okay, so it is like a worm, and the dislocation will move in the direction of the stress. And as you can see, after a certain point, so the dislocation will escape from the crystal. Okay, it will abandon the crystal, so no more dislocation. So let's remember that in that case, the dislocation is abandoning the crystal because there is no other dislocation in this crystal that hinder its movement. Okay. Concerning screw dislocation, so when we apply a stress on a crystal having this defect, so the dislocation area will move perpendicular to the direction of the stress. So in this representation, we apply a stress in that direction, and so the direction, the movement, the dislocation area will move perpendicularly to the direction of the stress. So in fact, if we consider the movement that is occurring to the dislocation and the direction of the slip, the Berger vector provides the modulus and the direction of the slip. So it is parallel to the direction of flow always. When I say direction of flow, I can either say movement of the material, but not necessarily in the same direction, because it depends on how the force is applied and the movement of the slip. So in previous classes, we introduced unit cells to describe crystal materials. And we defined that we observed that in some planes we have higher planar density, and we also observed that in some direction we have high linear density, high atomic linear density. And so now we can make a relationship with the slip plane and slip direction. So it is observed that for a particular crystal system, the slip plane is the plane that has the densest atomic packing, or in other words, the slip plane is the plane that has the highest planar density. Whereas the split direction corresponds to the direction in this plane, that is the direction that has the highest linear density. So basically, if I know my unit cell of my crystal, I identify the plane with the highest planar density, and so I identify the slip plane. And then, in order to know in which direction this slip will move, I identify the direction with the highest linear density. Okay, so that's why in the case of the zinc single crystal that has been plastically deformed, we observed that there was some different portion of the material that seems to be dislocated one from another. So certainly the slip plane were the planes that were in that direction, and they moved in the direction of the direction that had the highest linear density. Okay, so there is a relationship between the unit cell, the planar density, the linear density, and the dislocation movement. So regarding dislocation, all crystals have dislocation. It is practically impossible to create crystals free of dislocations. So the force that is required to move a dislocation depends on the type of chemical bonding, and depend also on the crystalline structure of the crystals. So it is dependent on the chemical bonding, because we need to break a chemical bond. So that's why for metal, it is generally the force required to move a dislocation is lower than in ceramics, because of the strength of the chemical bonding, and this also explains the fact that in ceramics, there is almost no plastic deformation, which means no movement that is possible for this dislocation due to the high energy of chemical bonding that are found in ceramics that are ionic bonding. Regarding the dependence of the force required to move a dislocation and the crystalline structure of the crystal, it is totally linked with what we explained on the fact that this slip movement and the slip planes are dependent on the linear density, linear atomic density, and linear plane density. So that's why we say we make this relationship between the difficulty to move a dislocation, which means the force required to move a dislocation, and the crystalline structure of crystals. In the case of metals that have been annealed, which means they have been submitted to higher temperature and they have been very quickly cooled down, we succeed to decrease the density of dislocation. So the dislocation density is about 10 at 5, 10 at 6 centimeter of dislocation per cubic centimeter, square centimeter, sorry. Whereas plastically deformed cold metals, that is the examples that we introduced at the beginning, we have a much higher density of dislocation. So we can play on the thermomechanical process to which the metal is submitted in order to control the density of dislocation. So now let's focus on interfacial or bidimensional defects. An example of such kind of defects is the grain boundary. So it is this region that separates two grains. And at this specific place that we call defect, the material has some specific characteristics. And so, for example, if we have a look to the corrosion phenomena, we will observe that the corrosion will occur particularly at the grain boundary, especially in the case of steel, stainless steel. And this is due to the fact that the property at the grain boundary are quite different from the properties, inclusively the material energy that is within the grain. So in a general way, corrosion starts at grain boundaries or other imperfections because of the higher energy level compared to the bulk material. So here we have introduced an interfacial defect, which is grain boundaries, but we are going to see that we have different interfacial defects that exist. So we are going to list all of them. So interfacial defects are boundaries that have two dimensions and normally separate regions of the materials that have different crystal structure or crystallographic orientations. So they are of different types. There are an external surface, which is a surface between the crystal and the surrounding medium. The grain boundaries that we've introduced, so the boundaries between two solid crystals of the same phase. Interface, which are boundary between two different phases. Twin boundary, we are going to see that is a specific kind of grain boundary. And stacking defects. So let's begin with external surface. So it is a surface between the crystal and the surrounding medium. And the atoms at the surface are not bounded to the maximum number of nearest neighbors. So they are in a higher energy state than than the atoms that are in the bulk of the material. And due to this fact, because they are in a higher energy state, so it gives rise to a high surface energy, which is quite equivalent to superficial tension, okay, that you may have studied in other kind of systems. And so to reduce this energy, the materials tend to minimize the total surface area. So, for example, the external shape of crystals is associated with lower energy planes. And so the surface energy can be calculated and can be measured, in fact, and it is expressed in joule per unit area. So the second dimensional defects are grain boundaries that we've introduced. So they separate the crystals of the same phase that have different orientations in a polycrystalline material. So as you can see on this representation, we have a quite big region of grain that is oriented in one direction. And you can see that above that one in this region, we have also the same crystal, but that is oriented with a different orientation, okay? And so this boundary region is called the grain boundary, and it has a thickness between 2 to 5 interatomic distances and is considered as a defect. And so as you can see on this representation and on the different kind of grain boundaries that are represented, we can have a look to the angle of misalignment between two grains, okay? So between the direction of two adjacent grains. So for example, between this grain and the one on the right right part of this representation. So the angle of misalignment is quite low. So we have a low angle grain boundary, whereas between that one and that one, okay, the upper right grain, so the angle of misalignment is higher. So we say we have a high angle grain boundary. So at the grain boundary, the atoms are less regularly bounded. They do not have the perfect number of neighbors. And so it results in a grain boundary energy, which is similar to the surface energy. And this grain boundary energy, is also related to the misorientation. So in the case of high angle, like that, in that case, a high angle grain boundary will have a higher energy than this low angle grain boundary. And so this is then directly related to their chemical reactivity. So grain boundary are chemically reactive and more chemically reactive than the region in the bulk in the middle of the grain. And so that's why, in fact, the susceptibility to corrosion is higher at the grain boundary, and it is even higher in the case of high misorientation. And another phenomenon that we observed at the grain boundary is that the impurity atoms preferentially segregate along this boundary. And so the question you can think about is the total interfacial energy lower or higher in a large grained materials or in a fine grained one? So which means is the interfacial energy is higher in the case of materials that have big grains, or in the case of a material that has small grains? Okay, so think about it and think about what we discussed about grain boundary, about the grain boundary energy, and about this grain boundary area. So what is the geometric shape of a grain? So the study has showed that in fact we have this kind of hexagons, or if we represent in 3D, we won't talk about hexagon, we will talk about tetrahedron. So it is this kind of geometry that enable to fill the space while maintaining the smallest area to volume ratio. So in this way, with this geometry, all the grains succeed to fulfill the entire space and satisfy the balance of interfacial tensions while minimizing the area to volume ratio. So to minimize this superficial area, and so the grain boundary area. And so when we observe such kind of images, if we use microscopy, okay, so these are common figures that we succeed to observe in metals. We should think about the 3D organization, the 3D geometry of the metal, which is much more like that, okay? So another defect is twin boundaries. It is a special type of grain boundaries that separate two regions with a mirror-like symmetry. As you can see, in that case, so there is a perfect symmetry between this part of the crystal or this grain and that grain, and the planes that separate these two grain is called the twin plane, and it results from atomic displacement due to applied mechanical shear force, or during annealing, which is when we increase the temperature of the metal and we decrease it very quickly. So it is annealing heat treatment, following by deformation. So in that case, we provoke this kind of dislocation, okay? And this creates such kind of symmetry in the material between these two grains, okay? So it is a specific kind of grain boundary. And when we observe a metal that has twin boundaries, so we observe these very particular shapes. So this is obtained by optical microscopy, and you can see that there is relatively straight regions with parallel sides, and they have different visual contrast than the untwisted regions of the grains. And so we can recognize in that case these twin boundaries right here in this material, because they have these specificities. Okay, and the last bidimensional defect that we are going to see is the stacking defect. So it occurs in materials when there is an interruption in the stacking sequence, mainly in FCC and HC crystals. So for example, in the case of FCC crystals, we should have this sequence. So ABC, ABC. So you can see that right here we have a perfect stacking sequence. Here also, but in the middle we have a stacking defect. So we don't have ABC, ABC, but we have AB, ABC. And we can also have such kind of defect in HC crystals and so on. So it's another kind of bidimensional defects. And finally, there are interfaces that are boundaries between two different faces, which mean these two faces have different composition and different crystal structure. And at this interface, we can have a coherent, semi-coherent, or incoherent interface. So in the case of coherent interface, we have a continuity of the organization of the atoms through this interface. So as you can see, in that case, it is quite organized as this interface. So it is an interface of low energy, whereas the extreme case is incoherent interface in which there is a large defect. The atoms close to the at the interface do not have the perfect number of neighbors at close distance, and so that's why, as we saw in this situation, we have interface of high energy, so with higher chemical reactivity and so on. And in the intermediate case, so we call this kind of interface semi-coherent. And finally, let's have a look to bulk defects that are generally introduced during processing and fabrication steps, and that are much larger than the other defects that we saw. So we have inclusion, that are foreign impurities, precipitates, that are agglomerates of particles whose composition differs from the matrix. We have phases that are formed due to the presence of impurity or alloying elements. So it is, for example, the case when the solubility limit is exceeded. And so a new phase of a new composition and crystal structure is formed. And porosity that arises due to the presence or formation of gases in the material. All these defects can be observed by microscopic techniques. For the inclusions, they are formed by foreign impurities, which is the case of copper oxide, that have been formed during processing and that are present in this high purity copper. So during the processing called laminated and reclosed and so on, these kind of impurities have been formed, and they are characterized by this more dark color. The porosity is also easily observed by electronic microscopy. So in this case, it is iron powders that have been compacted, and between these small particle of powder remains some void, so which are called pores. Here also, so you can see that in this second case, there is a small number of pores, because the material has not been only compacted, but it has been only submitted to high temperature. So this particle could melt and fuse together, and so it reduces the porosity of the material. The phases which are formed due to the presence of impurities or alloying elements can also be observed. So in that case, we see that the microstructure is composed of veins of graphite in pearlite matrix. Okay, and if we have a look to this phase, it is called pearlite. We will observe that each of these grain consists of alternate lamella of two phases. One is ferrite or iron, and the other one is cementite or iron carbide, so different compositions. And so it is an example of different phases that are observed and that are bulk defects. Okay, so now you know the different kinds of defects that exist in crystal structure. We saw point defects, vacancies, self-interstitials, and impurities. Then we introduced linear defects, edge, dislocation, screw dislocation, mixed dislocation, and we saw the relationship between plastic deformation and this kind of dislocation. After that, we introduced interfacial defects, external surface, grain boundary, twin boundary, stacking defaults, and interfaces. And we saw that, for example, these interfacial defects are directly related to corrosion and to chemical reaction or chemical reactivity. And finally, we introduced the bulk defects, pores, crack, inclusion, phases, and so on. So thanks to this class, we saw the relationship between some of these defects and materials properties. And along the presentation of this defect, we used images that has been obtained thanks to microscopic techniques. And so the microscopic techniques, either optical microscopy that I'm sure you already know, or electron microscopy techniques that use electron to analyze the surface of the material, allows to observe this defect in crystal structures. So hope you have learned a lot about imperfections in solids or defect in solids. And if you have any question, you can send me an email. Thank you very much, and see you soon.